Thank you for the introduction. Today we'll be talking about the expanding portfolio of new space solutions available to serve your mission goals and how you can influence what comes next. For today's agenda, we're going to frame the opportunity of what new space is in combination with the unique value that Microchip brings and how this is going to shape and affect how we're going to work together to solve some of the Earth observation challenges out there. After we've discussed the concepts a bit, we'll switch to the results of some of our space solutions to date and then close with how to best engage with Microchip. So let's start the conversation today about what is new space. It's not about a particular orbit or a specific mission goal or radiation tolerance level. It's really about the commercialization of space. And really what's happening here is if people are being forced to reinvent the supply chain, it's causing a different design mindset. People are trying to balance the cost versus the radiation tolerance versus the availability and repeatability of certain parameters. Everything is kind of being looked at from a different perspective. And what's behind this concept of new space, this commercialization, if you will? It's really about the changing economics. So if you look at what's happening here, there's been a reduction in the costs that are now opening space up for new applications. And these new applications are driving additional volumes, which in turn is driving costs down. So we have an iterative effect going on here that's really very quickly changing this market. So let's talk about a particular set of numbers here to put this into context. So the satellite launch itself, which really is all overhead to the ultimate commercial goals. The idea of actually just putting the satellite itself into space is not adding any value. If we look at what that overhead, that cost structure has looked like, it's been in the $200 million range. It's already come down by a factor of 4. And we're seeing a forecast to bring this down into the $5 million range. One of the driving factors of this is the idea of reusable rockets and also sending multiple smaller satellites on a single rocket into space. But if you think about the effects of going from $200 to $5 million from an overhead, it really does change the dynamics. In parallel to that, we're actually seeing the cost of the satellites themselves go down dramatically as well, from as much as $500 million to $500,000, or 100x change. That has to do with a lot of different factors, some of which we'll talk about today, is the increase in the available semiconductors to support these mission goals, but also the size, the function of these satellites are moving targets as well. If we put this together, the new space market is being forecasted as the next $1 trillion opportunity. That'll become very important later in this conversation to what's influencing all of us to take the right next steps. Let's look at what Earth observation is for a second. It's really defined as measuring the electromagnetic spectrum, which in turn provides insight into a number of different areas, including weather, geology, hydrology, and many more. This is something that's really interesting because not only is it bringing a certain scientific set of parameters that's driving a lot of innovation, it also has some very large social and economic effects beyond just the data itself. So let's think about what these return on investments are for a second. The idea of being able to go off and to have a weather satellite give you more insight into the weather doesn't just change our daily lives as far as whether we should head to the beach or find some other activities for the day. It really has huge economic impact if we can avoid a lot of damage caused by some of these catastrophic events. You can do the same type of calculations, whether it's on crops or minerals. Also affects things like the polar ice sheets and the ozone that's affecting global warming and potential flooding. These have huge economic results. So I bring this up again because you've got the changing costs of new space in general, but you also have the interesting dynamic around Earth observation where there's huge ROI to trying to capture this data. And what that really means is people are willing to offset those launch costs and to put a higher dollar satellite in place sooner rather than later to try to offset some of these economic results. So just some examples here. Here's a visual illustration of a bunch of satellites from a NASA perspective. This is looking at it purely from a government, but not necessarily the private. And a similar visual here from an ESA perspective, which is organized by type. Really the points I'm trying to get across here is this is a global initiative, and there's both government and private investments that are going to drive the activity. And I'm sure many of you on the line here today represent solutions to solve both those government and those commercial ventures. So how does this tie into the semiconductor market? Well, as you can imagine, your needs roll back to drive our set of deliverables. So for Earth observation, you guys as a group are driving a lot more data in the satellite and back to Earth. What that means is we have to make sure that we're keeping up with these particular data requirements. So from a connectivity point of view, we're seeing a shift to Ethernet to give not only a standard set of data requirements, but also something scalable. And we're also seeing a big shift to do a lot of pre-processing to make the best use of any downlink capabilities. We're also seeing a set of requirements come to us to support these shorter mission goals that you have. But this is not eliminating the environmental challenges of space, it's just changing where that bar is set. So we're seeing a much stronger focus on a set of radiation tolerant types of solutions versus Rad-Hard devices themselves. So why Microchip? Well, we've actually got several unique capabilities. First of all, we're a very broad, very high volume commercial company. We've got a number of processors, connectivity, and security solutions that we run at very high volumes, and we've also got a number of very cost-sensitive sets of requirements around this. What that means is we've got solutions that can hit the most cost-effective markets out there. But we're also a leader in space. In fact, we're 2 to 3x the next competitor in the semiconductor market. So what that means is we've got very strong flight heritage, very strong radiation expertise, and a portfolio of QML devices. So given that we have this commercial and space leadership, what we really are talking about here today is how we can leverage both of those in combination to really come up with a customizable set of solutions to service this new space market. So to give you a little bit of background to our commitment to space, I'll take a break here for a moment and show a short video.
Microchip has been a key supplier of space-grade components for over 60 years, with spaceflight heritage on hundreds of spacecrafts. Recently, Microchip has announced RT PolarFire, a high-density, high-performance radiation-tolerant FPGA with power saving of up to 50%. Also, Microchip is now shipping radiation-hardened FPGAs in plastic packages for low-cost, high-volume satellite constellations. With a strong background in custom and standard IC design for space, we boast an extensive flight heritage using our telemetry, motor control, and power protection solutions that drastically reduce board space and weight, increase reliability, and simplify space electronics designs. Our offering continues to expand into new capabilities on all fronts. Whether your application requires computing, sensors, communication, storage, motor control, or robotics, Microchip has solutions for you. Our standard power products portfolio includes linear and switching regulators, both isolated and non-isolated, ideal for powering space electronics and systems. Our highly skilled and experienced engineering teams also develop customized solutions to meet exacting needs. Voyager 1, the furthest man-made object from the Earth, has been utilizing our frequency control products continuously for the past 42 years to aid in the transmission of data from a distance of 13 billion miles. Our precision crystal oscillator platforms utilize state-of-the-art design, manufacturing, and control systems to meet the demands of exo-atmospheric flight and exceed customer expectations for reliability, performance, and value. Microchip's frequency and timing systems offers a broad selection of high-performance space-qualified crystal oscillators and atomic clocks delivering to key programs, including GPS-2 and GPS-3 satellite constellations, and space-based missile defense satellites. Frequency and timing systems also offers the world's first commercially available radiation-tolerant chip-scale atomic clock, bringing the accuracy and stability of atomic clocks to commercial space applications. Having been to the Moon, Mars, and beyond, our Rad-Hard Discretes and expertise behind them are an enduring design partner. Microchip continues to reach for the stars with innovative new products. Whatever your space mission, Microchip has solutions for you.
In the video, you heard about our strong portfolio of traditional space products. This entire portfolio could be leveraged for your new space applications around Earth observation, but as we've spoken about already, there's often a balance that's needed between some of the traditional mission goals and some of the commercialization goals. As such, in addition to this portfolio, which may be used for critical functions, we're looking to offer additional solutions. One of the ways we're trying to create that additional set of solutions for new space is to bridge between the traditional QML-based products and some of the commercial off-the-shelf solutions that are available. What we've recognized with feedback from folks like yourself is that oftentimes you're looking for that same set of radiation support, but you don't necessarily want to pay for a lot of the testing that's associated with some of the full qualification flows. As such, we've created some sub-QML flows that remove that testing, and that in itself can offer fairly significant cost reductions, closing that gap to the commercial products. In addition, what we've done is we've come up with variations that are using plastic packages. And these plastic packages offer yet additional cost reductions. So these two radiation design solutions without the testing and with different cost package solutions go a long way to bridging that gap and solve many of the problems for this new space market. But as I mentioned before, we're looking at this solution from two different perspectives. The other perspective is trying to leverage our very vast commercial portfolio and try to drive activity from that portfolio up to meet some of the space level qualification needs. What we're not saying here is that you take that commercial portfolio as is and move that into space. We honestly think there's a lot of risks associated with that. Rather, what we're advocating here is that by allowing us as a semiconductor vendor to apply our knowledge of the space market and offset some of those traditional gaps for that COTS set of parameters, we can find the right solution to serve your mission goals. Examples of that are things like traceability, radiation reports, or just downright support necessary to solve some of the technical challenges that you may be facing in a space environment. So really what we're proposing here is to focus on a scalable set of solutions that bridge from that COTS arena up to the full QML by offering both an RT and Rad-Hard by design set of solutions for that new space market. Leveraging both plastic and hermetic packaging, we think this is the best overall solution. So let's talk for a minute about the differences between these radiation-tolerant devices and their commercial counterparts. We're actually starting from the exact same data point, if you will. We're taking the same mascot, same functionality, same development tools, development boards themselves. Everything is available. So there's huge leverage that comes from tapping into these commercial solutions. But what we're doing is taking a look under the hood at the actual recipe that's used to build these components. And we're making subtle changes to the process that can have big ramifications for the susceptibility to certain types of radiation. So by tuning those critical parameters, we can create a solution that will help solve your solutions. And it gives you that set of solutions in a scalable way, because again, you can leverage all of the benefits of the commercial devices. You also have the ability of utilizing plastic packaging, but we're also bringing certain ceramic packages together into this market as well for those that choose to use the ceramic packaging as well, which wouldn't be available in the traditional commercial offering. So it's this changing of the recipe that's critical to build that set of portfolios. So as a result, we really have the largest portfolio today of plastic solutions for space. And we're going to talk a little bit more about some of these different solutions in the upcoming section. So now what I'd like to do is hand the ball over to Ronan Dillon to talk a little bit about some of his products.
Hello, and thank you for this opportunity to promote Microchip's high-rate discrete solutions new space offering for discrete semiconductors. Today, Microchip's high-rate discrete solutions, or HRDS, is the biggest supplier of discretes to the aerospace and defense markets. We offer all technologies, including Zeners, Diodes, Shockeys, rectifiers, transistors, transient voltage suppressors. We offer these in both hermetic and non-hermetic packages, as well as in chip form. We are MIL qualified up to including space-grade product. We are also MIL qualified in a manufacture and supply of hybrid and power solutions. We can take silicon carbide technology, put it in hermetic packages, and perform screening based on the application's requirements. We have now also added Rad-Hard MOSFETs to our portfolio and offer a wide range of custom products for our valued client base. Although we sell a complete range of products to serve other markets, we believe our proactive investment in creating a Microchip new space line offers the best overall costs. We do not recommend using COTS for space, but welcome feedback to refine our offering as the Earth observation market evolves. The key point here is that we are starting from our heritage base, 50 years of supplying product for space application. So we take our product from our MIL qualified lines, we offer light touch screening, and offer products that will reduce cost, improve lead time, and reduce risk for new space applications. Within our product teams, we do recognize new space, and in particular Earth observation markets, are looking for solutions to support short emissions, higher volume and more cost-sensitive payloads, but still achieve mission assurance and reduce that risk. A key element when it comes to discretes, such as MOSFETs and bipolar junction transistors, is the effects of radiation on their performance. Today, Microchip's HRDS offers MIL-qualified, radiation-hard transistors and MOSFETs, and we can use that same die and offer it to new space as a solution to reduce risk of any radiation effects in the LEO environment. So at a high level, Microchip can support this market need with our Microchip New Space Quality Flow, MNS. We offer both hermetic and non-hermetic packages and many different device families or technologies in both silicon and silicon carbide. So Microchip's HRDS solution for new space programs. Several years ago, we set ourselves an objective to proactively serve the evolving new space market. Results of this effort is Microchip's new space product line. With our products, we can support a wide range of functions with different mission goals. We offer a number of variations to our underlying mill-qualified product. We have hermetic and plastic packaging, we have chip form, we offer high and low temperature testing 100%, we offer optional pin D testing, etc. We apply learning from our traditional space products to make sure we are not compromising your mission success when offering lower cost options needed to commercialize space. So our starting point is to take product from our mill qualified lines, apply light touch screening to remove potential early life failures, thereby reducing the risk to your mission. So, Microchip's new space, MNS flow for diodes and transistors, is built on the premise that we are taking products from space qualified wafer fabrication, assembly, and test lines. Through this approach, and with light touch screening, Microchip's new space flow can achieve up to 66% cost reductions over standard GNS space qualified products. Of course, volumes are important here. So what have we achieved to date? Today, we are already supplying Microchip new space product. For example, we have an MNS 2N2907 AUB small signal PMP transistor. This product was built and tested on mill certified lines. And we have built it using a chip that is radiating hard and tested and guaranteed for low dose radiation testing up to 100K rads. We have performed light touch screening on this product, which includes 100% testing at high and low temperatures, as well as PIN D, our particle impact noise detection testing. We have seen keen interest in our non-hermetic plastic Rad-Hard MOSFET. This is a MOSFET product that is built in a plastic package using die that was fabricated in our 6-inch wafer fab in Colorado Springs on the US mainland. This die has been tested to radiation hardened single event levels and TID levels 100K rad. We offer this in a TO220 and T2 pack, and again with light touch screening, or indeed full screening if required. So overall, Microchip's new space flow offers a broad portfolio of packages, options and devices. With radiation hardened die, 100% hot and cold electrical testing, controlled baseline or certified product lines, and indeed an enhanced obsolescence policy, as you would get with all high-rel discrete solutions from Microchip. I also want to take this opportunity to promote Microchip's Rad-Hard MOSFET offering. We are now DLA certified on 2 part numbers from MilPRF 9500/746/sheet, both the 150 volt and 250 volt size 3.5 die. This product is built using die that was fabricated on our 6-inch wafer fab in Colorado Springs on the US mainland. Over the coming months, we will complete the qualification of the part numbers from that slash sheet and also from /753 and /760. We are delighted to say that our product has showed improved efficiency based on lower RDS on and gate charge versus our competitors. And more importantly, we have seen improved radiation performance on these Rad-Hard MOSFETs over our competition, both for TID and for single event. So here is a list of the products that we have qualified and indeed plan to qualify over the coming months. Today we are qualified and can offer 2N7593U3 and 2N7589U3. Over the coming months, we will complete the qualification over these 3 slash sheets. Next, Ken O'Neill, who will talk about our FPGA solutions.
Thank you, Ronan. Hi, I'm Ken O'Neill, and we'll now take a look at FPGAs in new space applications. Our discussion on FPGAs for new space applications begins with our current radiation-tolerant FPGA portfolio. 4 of the 5 product families represented here, RTSX through RTG4, have been qualified to QML levels and have successfully performed on many space missions, in some cases for more than 15 years. The 5th and most recent FPGA family, RT PolarFire, is going through QML qualification currently. We know that new space applications rarely seek QML qualified components. However, this heritage is important to set the stage for the discussion on how Microchip's approach can help designers of new space systems. Our objective in creating a product line for new space applications is to reduce cost of acquisition and to reduce manufacturing lead times. We have 2 ways of achieving these goals. Firstly, by offering our radiation-tolerant FPGAs in ceramic packages with less screening and less paperwork, we're able to accomplish savings in both manufacturing cost and cycle time. Secondly, for the RTG4 FPGA family, by investing in the development of a new plastic package, we've been able to achieve even greater savings in manufacturing cost. All 4 of the product families which are currently QML certified are available as sub-QML parts. RTSX, RTAX, and RT ProASIC 3 are available in ceramic packages only, whereas RTG4 is available in both ceramic and plastic packages. The most recent product, RT PolarFire, is still going through QML qualification, and our roadmap for a sub-QML version is not finalized yet. So here we take a closer look at sub-QML FPGAs. Sub-QML FPGAs use the exact same silicon as our traditional QML qualified FPGAs, and with one exception, they use the same packages as the traditional QML FPGAs. The one exception is RTG4, which is available in a plastic package, as well as the traditional ceramic package. Where sub-QML FPGAs deviate from traditional QML FPGAs is the screening, testing, and paperwork. We have 2 sub-QML screening flows. The first flow, called reduced flow or R flow, actually has all the same screening as a QML class Q FPGA. However, it has significantly reduced paperwork. The second flow, military temperature flow or M flow, deletes a lot of the mil standard or QML screening from the manufacturing process. In both cases, the paperwork accompanying products is reduced, which adds to the cost saving. To address the requirement for sub-QML RTG4 FPGAs, we've introduced the plastic 1657 ball grid array. This meets the needs of high-volume satellite constellations requiring lower pricing than traditional QML qualified components. The 1657 ball grid array is pin compatible with the 1657 ceramic column grid array, and it has completed its qualification to JetX standards. All plastic RTG4 FPGA flight units are tested at hot, cold, and room temperature, and a selection of documents are available for designers considering the plastic package. Our new generation RT PolarFire FPGAs bring higher levels of density and performance than we've been able to offer before, saving system cost and engineering effort by virtue of their low power consumption and freedom from configuration upsets. They will be available with QML Class Q and QML Class V qualification. The plan for sub-QML RT PolarFire FPGAs is being developed currently, so stay tuned for additional information. Here we look at the role of FPGAs in artificial intelligence and machine learning applications in new space. The challenge that satellite designers face is one of increasing demand for information gathered on orbit. Sensor resolutions are increasing, frame rates are increasing, and now satellite payload instruments are generating hundreds of gigabits per second of data. Downlink bandwidth is not increasing as quickly, which means that sensor data must be processed and turned into useful information in the payload instruments. So to do that, you need bigger, faster FPGAs with more features, such as our PolarFire FPGAs. You also need sophisticated artificial intelligence and machine learning capabilities to enable efficient processing and autonomous decision-making on orbit. Convolutional neural networks are commonly used for image processing systems. These networks are developed and trained on the ground and optimized for deployment in inferencing application space. In space, FPGAs are often used to host the neural networks as they provide flexibility to modify the network in development and in deployment, while at the same time providing sufficient processing resources to provide a significant power performance benefit relative to general purpose processors or graphics processors. So this slide shows the VectorBlocks AI solution for Microchip. This includes the VectorBlocks Accelerator SDK, or Software Development Kit, and the VectorBlocks Neural Network IP core, which runs on PolarFire and RT PolarFire FPGAs. The VectorBlocks Accelerator SDK accepts networks from multiple input frameworks and produces a common output representation. Networks created in TensorFlow, Caffe, ONNX, Keras, OpenVINO, PyTorch, and Darknet can be directly input into the SDK flow. The VectorBlocks SDK performs a three-step process. Firstly, it will optimize incoming trained models, then calibrate them for scaling to 8-bit representations, and finally create 8-bit integer models that the core VectorBlocks IP can process in the FPGA. It also includes a bit-accurate simulator for early testing of quantized model accuracy and early application integration. There is a reference hardware platform using the PolarFire video kit, which uses a video camera as input and sends its output to an HDMI display. This tool flow allows software developers to create artificial intelligence machine learning applications for use in PolarFire and RT PolarFire FPGAs with no prior knowledge of the FPGA architecture, hence increasing productivity. The top table gives results for area and performance across the three size configurations of the core VectorBlocks IP with no triple module redundancy applied. The size numbers are listed in thousands of lookup tables, or LUTs, LUTs, as well as the percentage of LUTs available on the RT PolarFire FPGAs. The maximum frequency, or Fmax, determines the peak gigaops that the configuration can deliver. Power numbers are listed in milliwatts per gigaop. Performance is listed for two popular computer vision networks, MobileNet V1 and TinyYOLO V3 in frames per second. Power efficiency increases at larger size configurations. Performance scales well per gigaop. The bottom table shows some preliminary utilization and performance data with synthesized local TMR applied to the entire core VectorBlocks IP core. As expected, there is a decrease in performance of around 35% to 45%, and this is observable in the decreased peak gigaop rate and the lower frames per second rates. Power has not yet been measured for the TMR implementation. Note that no radiation testing has been performed on the core vector blocks IP, either with or without TMR, so it's not clear whether TMR gives any significant improvement in the accuracy of the IP in a radiation environment. And here we take a look at power consumed in PolarFire FPGAs for 3 different implementations of the core vector blocks IP. We have the dynamic power consumed by the IP running at peak gigaops, the static power consumed by the portion of the FPGA where the IP resides, and the total power. The final column in the table shows the total power normalized to milliwatts per gigaops. When we compare with deep neural network IP running on a competitor's FPGA, we see that vector blocks running on PolarFire offers a 50% to 70% saving in power at equivalent levels of inferencing performance, which is hugely significant in applications with strict power and thermal constraints, such as onboard data processing in new space systems. And so with that, I'm going to hand it back to Chuck, who will summarize some other microchip solutions for new space applications.
Thanks, Ken and Ronan. I'll now share some of the efforts from other BUs that weren't able to join us here today, starting with our processors that complement the FPGA imaging capabilities you just heard about. I'm going to highlight one of our processors, the SAM71. The reason we'd like to highlight this is it really gives a broad set of capabilities to solve some of your problems. First of all, from a processing point of view, with an M7 300 megahertz core processor delivering 600 DMIPS, this is something that can serve some of your system needs as well as your data imaging needs, whatever the case may be. It also has connectivity, security, has the ability to have on-chip memory or to establish external memory capabilities, all in a compact package in ceramic and plastic offerings. So we're highlighting this because we think this is going to be a strong performer in that market. But the other reason we're highlighting this is it's a great example of scalability. This solution has been available in the commercial market for some time, and complete set of development tools, evaluation boards, what have you, that are available there. And we've made an RT version that I just spoke about, but we also have a Rad-Hard by design version that's designed for more deep space applications. So the fact that we have a solution that scans all of these capabilities really gives you unique processor scalability for this new space market. What I'm talking about here is you can start your design with very low cost, readily available COTS evaluation boards and tools. You can then build some of your early internal prototypes using some of those COTS devices, and then you can transition through to your flight model requirements using the RT parts, using the same plastic package. And you can also leverage ceramic if your needs require as well. You're getting all of that software compatibility, access to application notes, everything that you can benefit, along with a full set of radiation characterization available to support your needs. In addition to that one particular processor, we have several other RT processors that have very strong flight heritage with over 30,000 plastic flight models that have been delivered out into our customer base to date. We also have a number of Ethernet solutions. This 5, for instance, was just released to the space market, and we've seen this very quickly become a very high-performing part, being our second largest revenue generator for the space market in just a couple of short years. The reason we talked about before is you've got that scalability, and you've also got the commercialization of space that's going on, where everybody wants to design their imaging products to be able to plug into different bus situations where they don't have to worry about unique connectivity. It also gives people the opportunity to design systems that could be used for non-space applications as well to get additional scaling economic results. We also have a portfolio of memories. Here is an example of a parallel 64 megabit flash memory. We've got a serial version of this memory and also a small EEPROM option. Again, all of these memories offer the commercial and the space versions. Let's take a minute to talk a little bit about some unique products that were designed for the space market itself. So here we've got some system managers that are companions to our FPGA or processor environments. And you can visually see here the boards connected together. So let's talk about the LX7730 for a second. What's really great about this is you've got strong integration, right? So you've got 12-bit ADCs that are all put into a single package along with 10-bit DACs. You've got everything that you need to solve some of your system level problem in a very small ceramic or plastic package versus building this out of all the different discrete pieces. The good news is we also service all those discrete needs, but we really challenge you to take a look at this because we think this is going to give you not only savings in power, weight, and size, but also time to market. We've got a similar device that's set up to target some of the motor control pieces of your market. So for an imaging, oftentimes you have multiple motors to control the positioning of your imaging device. So this again gives you tremendous integration, value, time to market solutions. From a timing perspective, we also have a very, very broad portfolio of devices, and we've taken a number of those into the traditional space market, but we're continuing to expand that, focusing on this new space market. So here you can see we've highlighted a couple of examples with those lower radiation, lower cost solutions. One unique product that's maybe something that would be of interest to look at is this new space atomic clock. So this is something that traditionally has been used for government satellites to deal with anything where you're in a GNSS denied situation. But the commercial aspect, there could be lots of value propositions for this increased accuracy as well as far as servicing your end market needs. If we look at some of these products together, and I'm using the timing examples here tied to application notes to the processor, FPGA, Ethernet, and different other processor solutions that we have out there in the market, you can see that we're really trying to look at this not at a component level, but try to solve your overall mission goals. So hopefully between what I've just talked about and Ken and Ronan, you've got a sense for the portfolio that we have today. But really what we want to work with you on is how do we go to that next level to continue to service this fast moving market. So how can you engage with Microchip? What we're hoping to gain from today's conversation is the attention of some disruptive partners to work with us to refine what products come next. We have a number of different solutions that we can continue to add options in a sub-QML area, as well as add radiation performance to our commercial portfolio. But the good news, bad news to this is we've got an overwhelming set of choices, and without customer insight, it's almost impossible for us to make the right solutions available to you in a timely fashion. So what we're asking you to do is to reach out to us, leveraging our aerospace and defense homepage on microchip.com. You'll find there a box to schedule a call with our team. And although this is set up to service a number of different needs, if you just check the boxes to service aerospace and defense and just fill in that this is a follow-up to the webinar discussion to talk about our new space roadmap alignment, we'll be able to schedule a call with you and our subject matter experts to have this conversation and try to set the priorities moving forward. As was mentioned, there's also some resources that are available to you today. You'll see a number of things listed in your screen, an example of which is the Space newsletter, which we encourage you to sign up for, as well as an article that summarizes our view of the new space market that might be helpful to talk about internally with some of your peers. So with that, I'd like to turn it back over to Dave to see if we have any questions that we can try to address here with our panel today.
All right, very good. Yeah, we sure do, guys. A few people have submitted questions, so we'll jump into those in a second. If you'd like to submit a question now, please type that into the Ask a Question box and hit the send button. Also, please take a moment to complete the feedback form that will appear on your screen at the end of the webinar. All right, the first one I'll ask is, let's see, well, what about outgassing of plastic packages? So how do you handle issues with that?
So I'll talk about that generically, and then Ken and Ronan, please chime in with your additional thoughts. This is an example of some of our space heritage, and what we've been doing here is with a variety of customers, we've been looking at the requirements that are out there, both in the industry as driven by folks like NASA, and work to produce some of the data that's necessary to support some of those things. One of the things that we're striving for is to see if there's some consistency out there that we can have a more standardized way to go off and solve those problems. So frankly, we're doing some of this on a case-by-case basis, but we welcome your inputs on trying to better design those standards.
Yep, I agree, Chuck, with your comments there. First of all, there really are plastics flying out there in space. I suppose that's the first thing to note, right? From my experience, the satellite manufacturers will look at things like coatings and so on to protect from outgassing. Obviously, location of the product where they are in the circuitry in a satellite is important. You're not going to put any plastic parts or any outgassing material near optics on a satellite, for example. It's not going to happen. But my main point is it's already been used out there, and we have supplied GENA screened or space screened plastic parts already for certain applications. For example, inside in a space station where it's a benign environment for plastic for obvious reasons. But yes, so it is already out there. So also we can actually perform the outgassing tests as required and see what the measurements are and so on our product.
Okay.
Yeah, this is Ken. Sorry, I was while Ronan and Chuck were speaking, I was looking frantically to see if I could find the NASA outgassing spec number. I wasn't successful, but I can tell you that the RTG4 plastic package was assessed for outgassing and found to be compliant with the NASA spec for outgassing. I just can't find the exact spec number on the fly here.
Oh, that's okay. There are a few of them, I think. Okay. Let's see. What I don't know if you're comfortable discussing this, but I'll ask it anyway. What competitor FPGAs were you comparing against?
Yeah, usually on public forums like this, I don't like to disclose the name of competitors. There's really only one competitor who has rad-tolerant FPGAs in the marketplace at the moment, and it was that competitor.
Okay, I think I know who you mean. Hold on a second. Okay, do Microchip's SoC systems have a primitive similar to the Xilinx block frame_ECI2, providing permanent control over the FPGA's configuration register?
Yeah, so there's really kind of a two-part answer to that question. The first part of the answer is the FPGAs that we have. So there's the historical traditional space FPGAs, RTAX, RTSX. Those are one-time programmable, so there's no need for a configuration stream to be uploaded into those parts in space. or even on the ground because the parts are just not reprogrammable. The more recently introduced parts, RT-ProASIC 3, RTG4, and RT PolarFire use a reprogrammable technology. RTG4 and RT PolarFire are supported for reprogramming in space. So you could argue that, yeah, okay, there's a real use model where a designer or a satellite operator could upload new configuration code to the FPGA. So there, within the context of reprogramming the FPGA, there are a series of fault detection systems built into the FPGA and built into the programming mechanism. In the case of reprogramming the part in space, we would recommend customers use a direct C configuration programming approach, which is something that is a Microchip proprietary thing. It's code that runs on a processor that sits adjacent to the FPGA in space. Direct C and the programming circuits in the FPGA have error checking and error detecting capabilities. There is not a primitive comparable to the Xilinx primitive that was referenced in the question because it simply hasn't been needed because of the error checking and error handling that's built into the FPGA.
Okay. Next one. Can you offer a rough timeline for the sub-QML RT PolarFire program?
Yeah. So sub-QML RT PolarFire, we expect to have a plan certainly within the next 6 to 9 months, and we would expect to have a sub-QML RT PolarFire product somewhere in 12 to 24 months.
Oh, okay. Pretty quickly. How about single event gate rapture events? How do you mitigate those in PowerFETs?
Ronan, would you be able to?
If you're talking about the Rad-Hard MOSFETs, or
that's what the question. The question
yeah,
references.
Okay. Yeah. So regarding Rad-Hard MOSFETs, obviously we're not going to talk about our secret sauce, but basically the offering that we're looking at for Microchip New Space is to take our existing space qualified Rad-Hard die and put it in package and subject it to the required screening for the application and offer that as a solution. So there will not be so the mitigation is by using Rad-Hard qualified die in the package.
Okay.
If that answers your question,
yeah. What's the lead time for the RT parts compared to the COTS versions?
I'll try to take a cut at that. You know, that's obviously a very broad question of a bunch of different products. But interestingly, in this market, we've seen that the lead times are very good on some of our space products, just because of the nature of how we build and manufacture those and trying to leverage traceability and a finite number of lots. So we've actually had several customers, due to the scalability, move up in the traditional environmental requirements to try to get better availability. That's more of a short-term situation with the given, semiconductor industry today. But one of the things that we have done with the kind of shift to new space is we've looked about these products very differently. So we're changing some of our thought processes as far as using different logistics channels to try to build inventory in different ways, to offer very short lead times on some of the initial products themselves for prototyping. And even some of the flight models, we're doing some unique things about building up inventory, because instead of having single digit, we're seeing folks that are interested in tens of units or even hundreds of units fairly quickly. So we're seeing a shift, and you're going to see lead times be much lower than historically for this class of product.
Okay. I guess we got time for one more. You mentioned that Ethernet is a popular protocol. Do you see that replacing other protocols? And a follow-on would be, do you offer Ethernet switches that are qualified for space applications?
Yeah, so as I mentioned before, we've seen a very quick uptick. Part of that is through some of the efforts around the Lunar Gateway, but we see that trend continuing. But this goes to our really request to talk with some of the folks on the line here today. So although we're very confident that over time, Ethernet is going to become the dominant connectivity interface and replace a number of different things, the timeline that that's going to happen and the overlap where people may need to support, Ethernet and something else, we're very interested in getting additional data points on to guide us. And with the increased use of Ethernet in general, driving the additional data that's moving around in space, we do see that there's going to be a need for, switches, at some point in the future. This is another question that we're struggling with is, we're looking at both gigabit and 10 gigabit Ethernet, but the timing for some of these things, we're not sure, because the recipe that you guys are going to be looking at for how much pre-processing you do in space versus downloading that information, I think there's a lot of opinions and thoughts out there. So we very much need to do it. The good news is, similar to what was talked about with the FPGA, our ability to react, because we're leveraging existing commercial offerings here from the Ethernet, is pretty quick. So this is not a ground-up design effort in many cases. So, we want your near-term input. We want to try to have these products available when you need them.
Okay, very good. And with that, I'm afraid we're out of time for today. For those questions we didn't have time to answer, we'll be getting back to you via email. And so that'll conclude today's presentation. On behalf of Electronic Design and Microwaves and RF, I'd like to thank Avnet and Microchip for sponsoring the event, and of course, all of you for joining. Have a great rest of the day.
Thank you.
Thank you.
Thank you, everybody.